Hello. Today I'll be talking about figure eight. And in figure eight, we see tonic, which is 1 to 4 hertz, and phasic 10 to 30 hertz optogenic stimulation in response to salient stimuli and motivational demands that suppresses and enhances the SC evoked PSP respectively. How the tonic and phasic dopamine release modifies the hippocampal synaptic activity was investigated here. Dopamine neurons continuously shift their firing rate between tonic and phasic modes in response to the stimuli. Bath application of dopamine did not reproduce temporal and spatial profile of dopamine release through tonic and phasic firing of the VT SNPC inputs, interestingly. A dual action of dopamine could thus explain the large variability in the response to the Bath applied dopamine in individual CA1 PNs. There's complexity in the involvement of different receptors and hippocampal projections that play a role. It's also possible that a high density of dopamine transporters or metabolic enzyme prevent Bath-applied dopamine from reaching its SC and inhibitory neuron targets. In the ventral striatum, the tonic mode of DA release maintains low basal dopamine levels sufficient to activate the high affinity D2 type receptors, but not low affinity D1 receptors. To simulate the effects of more natural patterns of the VTA, they tested with distinctive bouts of tonic and phasic firing and found an impact on the SC-evoked PSP and CA1 PNs. In A, we can see in the experimental setup of the VTA SNP axon, so you can see here in the simulation paradigm. And the IC was simulated at the CA1 PN neuron, and the Schaefer collateral synapses were simulated as well. B is showing the effect of tonic and phasic optogenetic stimulation on the SC-evoked PSP. The tonic optogenetic stimulation occurs underneath the blue bordered bar, as you can see here, consisting of 5 ms long pulses of light given at 1 hertz. The phasic optogenetic stimulation consisted of the 25 burst protocol applied at the 10-minute mark that you can see here with the red line. And as we can see, the PSP amplitude increases with the phasic stimulation and the SC responses through a D1, D5 receptor-dependent enhancement of excitatory transmission. C shows the traces at key phases of the experiment, where the black trace represents the baseline, the blue represents the end of the tonic period, and the red represents the end of the phasic period, mirroring the amplitude differences that we saw in B, shown in a different form. And D shows a summary data of the mean fold change of the SC-evoked PSP from baseline following tonic and phasic photostimulation. The tonic optogenetic stimulation suppressed the SC-PSP to about 65% of the baseline, similar to the effect seen with single burst photostimulation. And the phasic phase following tonic stimulation resulted in a net increase in the peak PSP depolarization to 137% of the initial baseline value. Low levels of dopamine release stimulating tonic dopamine neuron firing depress the SC response through a D4 receptor-dependent enhancement of feed-forward inhibition mediated by the PV interneurons. Patterns of optogenetic release, more similar to the tonic phase firing patterns of VTA dopamine neurons, suggest opposing bidirectional effects on the efficacy with which the SC inputs excite their CAPN targets. One possible explanation is that D4 receptors may not be effective during prolonged photostimulation as they get desensitized in response to high dopamine levels. Absence of a suppressive effect on the PSP with stronger dopamine release ensures that the SC-evoked excitation of the CA1 PNs via phasic dopamine firing and release local levels will be unopposed by suppressive effects on the SC excitation by tonic firing. The different firing patterns and balance of excitation and inhibition at synapses and selective anatomical distributions of projections influences timing, which modulates activity of the dopamine receptors, balance of LTP, and also synaptic plasticity. Recordings from these brain areas suggest that reinforcing action of dopamine is associated with the transition from tonic firing mode, where dopamine neurons fire at single spikes at low frequency, to burst firing, where the dopamine neurons fire at high frequency. This shifts the modulator tone from inhibition to facilitation of the SC enhancement inputs, thereby enhancing mnemonic information flow through the trisynaptic path while leaving the PP input unchanged. Phasic patterns of in vivo optogenetic stimulation of the VTA afferents in the hippocampus, as we see, enhances memory storage and recall as well as learning. And these studies show a more physiological relevant spatial temporal pattern of transmitter release from the VTA and SNPC dopaminergic hippocampal inputs. Thank you and apologies for the virtual presentation.